We are going to discuss about timing metrics for sequential circuits. So before that, we have to discuss what is combination circuit. Okay, so the combination circuit is nothing but a full adder, half adder, and drop. Okay, so if this is a combination logic, okay, if this is a combination circuit means here the current the output of the logic. Okay, so the output of the logic is a function of the current input value, right? But all the useful systems which will require some storage of state information. Okay, so which will leading to the another class of circuit which is called as a sequential circuit. Okay, so the sequential circuit it has a memory. Okay, so it not only depends upon the current value, it's also depend on the, so this is my register and this is D input and if I have Q. It not only depends on the, it is in a state and this is in my current state.
Yeah, okay.
So it depends on not only on current value but also upon proceeding input value. So the sequential circuit which is having memory. Okay, so if you see that so this is a general block diagram of the final state machine. Okay, so here you have a block. So this is a block diagram of finite state machine. Okay, using a positive edge trigger register. So
this
system is belonging to the class of the synchronous sequential system. Okay, which is whereas in which this resistor is under the control of the single global clock. Okay, so this output of this finite state machine is a function of the current input and the current state. Okay, so this next state is determined, which is based on the current clock's current state and the current input. Okay, so this next state is output is based on the current input and the current states. Okay, so you know what is positive edge triggering and negative edge triggering. So this is nothing but your positive edge triggering. So if this is a clock. Okay, so this is nothing but a negative edge triggering. This is a positive edge triggering. Okay, so and thus we are going to discuss about the timing metrics for this sequential circuits. There are three important things, important timing parameters. Okay, which is associated with this resistor. Okay, so the first one is setup time. Okay, suppose this is the clock I am giving to this resistor and D is my input. Okay, D is my input. So here for the next clock, this is a positive edge triggering, okay. So this is a positive edge triggering. So during the during this time, okay, so the data must be stable, okay. So you can see this is my data. This data is not changing during this time. So this is nothing but your setup time, okay. So and even after passing this the data should be should not it should not change. So that is called as hold time, okay. That is, the data must be stable, okay. So the first one is a setup time, okay. So it is defined as minimum amount of time before the clock activates, the data must be stable, okay, for it to be latched correctly. So this is a definition for setup time, okay. So this is my first parameter, okay. There is a minimum amount of time before the clock active edge, the data must be stable, okay. So what is the next one? The second matrix is hold time, T hold. So it is defined as minimum amount of time after the clock active edge during which data must be stable. Okay. So if there is any violation in the violation, okay. So suppose the data is changing during this period, okay. So it will result in the during this period it will result in the setup time violation, okay. So this is also called as delay constraint. Okay, this is also called as maximum delay constraint. So so it may cause us incorrect data to be captured. Okay. So if suppose the data is changing during this period, okay. So this will cause us hold time violation. So it's also called as minimum delay constraint. Okay, so this will causes incorrect data to be matched. So this setup and hold time, okay, hold time are measured with respect to active edge of the clock. So you have to note that the hold time may be negative. Okay. Okay. So suppose if the data is if it is not changing, okay, and you can see you have to get the output as Q, no? So this is your Q. So this Q you are receiving whenever the clock during this time, okay. So you can see it is receiving the data get received okay, this data. So this time is called as TCQ. So this is your third important parameter. Okay. Okay. So consider this is my system. Okay. This is my combination circuits and DQ, and the same clock I am going to give it for the second D flip flop. Okay. So
yeah, man, you go.
so what is TCQ? TCQ is nothing but whenever the setup time and the hold times are met, so this data D get copied to the. So these two conditions are met, the D get copied to the Q. Okay. So after this, so this is called as worst case propagation delay. Okay. And this one, okay, so this is called as TCCQ. Okay, so this is called as best case. Best case propagation contamination delay. Okay.
It's good.
So consider the circuit here I have given a global clock. So consider this is my clock. Okay. So whenever during the positive edge of the clock, the D1, okay, so the D1 will reach here, right? D1 will reach here, and whatever the input to this D2 reaches the output, okay, during this positive edge, okay. So this is my total clock period, right? So this is my total clock period, okay. So during the next clock edge, what will happen? Again, this D will the next data. So okay, one will reach here. Next, during this positive edge, the 0 will come here, okay, and this 1, okay, this 1 will reach here, okay. So this 1, it has to reach at this point, okay, at this clock, during this clock, okay. Suppose if you see, so this has to cross, okay, so this has to cross TCQ, right? TCQ. What is TCQ? The D1 data get copied to Q1, okay, so this one has to reach here. So for this one, you take TCQ time, right? Next, T propagation delay of this combination circuit, okay, this combination circuit, that is I can take this one as a TPD logic, okay. Then it has to get stable before this before the setup time, okay. It has should have a setup time, no? So TCQ plus TPD logic plus TSU, okay, that is equal to T, okay, TC, okay, that is equal to TC, or it may be the TC should be greater than or equal to TCK, okay. So what happens if this is less than TCQ? So if you see, assume that my TC value is 10, okay, 10 nanosecond, okay, and TCQ value is 5 nanosecond, okay. So then TPD logic values 4 nanoseconds, okay, and TSU is 2 nanoseconds. Consider if this is a case, okay. So this is nothing but 10 nanosecond, right? So this is 10 nanoseconds. So even before this TSU, the data must be stable, okay. So you can see this TSU values now it is 2 nanosecond, okay, 2 nanosecond. So it get reduced to 8 nanosecond, right? It get reduced to 8 nanosecond. So you can see this TCQ and the TPD logic is totally 9 nanoseconds. So it will reach only after this during it will come. It will not be stable, okay. It will not be stable before this during this setup time period, okay. So after 9 nanosecond only it is reaching. So it will end up in the, since it is reaching, it is violating the logic, okay. So it will end up in the metastable state. Okay, consider my data is changing during this period, okay. So it is changing during this period. Okay. Consider my data is changing during this period. It should not be changed, right? No. So since it is changing, this my Q. Okay. So my Q value it will not know. So it will go to the metastable state. So it will take some time. Okay, it will take some time to reach the output. Okay, to the correct output. Okay, so it will go like this. Okay, it will go like this, and it will end up in one stable state, one or zero, correct stable state. Okay, so this the time it is taking. Okay, the time it is taking to reach the correct stable state, it is called as resolution time. Okay. So if you see if it is 14 nanosecond, if it is 14 nanosecond means we can see. So this is 14. Okay. So this will be 12 nanosecond. So even after the 9 nanosecond, it will be reached and it will be get stable. Okay. So it will avoid the setup time violation. Okay. So here I can rearrange this equation: TCQ plus TPD logic, that is greater than or equal to TC minus TSC. Okay. So this is called as my arrival time. Okay. Arrival time, and this is called as required time. Okay. So in order to avoid this setup strain constraint, okay, the setup slack that is equal to, okay, the required time minus arrival time. So if it is positive means there is no problem. Okay. So if it end up in negative value means there is a problem. Okay. So this is also be written as minimum clock path minus maximum data path. Okay. So this will comes under the topic called static timing analysis. Okay. Static timing analysis. So it is a method of validating the timing performance of a design by checking all possible paths for timing violation under worst case condition. So next one is hold time analysis. Here we must ensure that So this is nothing but a launch flip flop and launch register, and this is called as capture. Okay, capture 1. So in hold analysis, we must ensure that the data launched during the current clock age,
Besides, guys, if I had you would go to the other you
okay, should not travel to the capture flip flop. To the capture flip flop. Before the hold time has passed after the clock age. Okay, so here you can see this T hold. Okay, the since this data is holding for some period. Okay, this data is holding for some period. Whatever the Q value, okay, this 0, the 0 should not reach here. Okay, so it should not reach this. So we have to increase the time of this. So you have to increase the value of this. This combination circuit. So I can write TCD TCD of this logic, okay, plus TCD of register. Okay, TCD of this register and this logic, okay, must be greater than the T hold time. So I can write this is my arrival time, okay, arrival time, and this is my required time. So since this hold time is independent of
touch
the clock, okay, and we have to note since we have to note this hold time is independent of the clock, okay. So this this is equal to arrival time minus required time. Okay, so if it is positive, there is no hold time constant. Okay. So hold slack time is nothing but is also called as minimum data arrival time minus maximum clock path delay.
it's all it's all
So if you see this setup time constraint, so if I increase this clock time, okay. So if I increase this clock time, suppose if you see here, this is 5 plus 4 plus 3, that should be greater than 14. Or this TC I can increase to 18 also. Okay. If I increase the TC to 18, okay. So what happens to my frequency? The frequency must be 1 by 80. Okay. So 1 by 18 is less value compared to 1 by 40. Okay. So in order to achieve the maximum frequency, I have to keep this TC value to 11. Okay. So if I keep this TC value to 11, then I can get F is equal to 1 by 11. Okay. So 1 by 11 is my maximum frequency. So this 11 nanosecond is called as my minimum time period. Okay. This will be my minimum time period, and this will be my maximum frequency I can achieve with this design. Okay.